이어서 저희 리퍼블릭 프로토콜이라는 프로젝트의 최고 기술 경영자 CTO이신 룽 왕님의 강연이 있겠습니다. 주제는 RenVM, A Virtual Machine for Privacy Preserving Computations라는 주제입니다. 박수로 맞아주시기 바랍니다.
Good afternoon, everyone. It's a pleasure to be here at Build All Seoul 2018. Over the last couple of days, we've seen some really amazing talks on privacy in particular. And today I'm really excited to be here and to share our work, which we've been doing quietly over the last couple of months, based on research that we've done over the last year, which has culminated in Ren Virtual Machine, a decentralized virtual machine for privacy-preserving computations. The takeaway so far has been that decentralized privacy is hard. And this comes down to two major reasons. The first is that in a decentralized network, your data is stored and replicated on untrusted nodes. We cannot rely on these nodes to behave or ask them to do anything in particular. And in fact, sharing and replicating data is required in many cases for these decentralized nodes to actually work. Now, there's a temptation to simply encrypt our data and then put that data on the decentralized network. But doing that doesn't solve problems of permission-based access. How can we let people access this information that weren't the ones that put it there without having complicated key distribution mechanisms? Secondly, we'd like to do computations over this encrypted data or over this private data. And again, these computations are done by untrusted nodes in our network, so we cannot necessarily rely on them to see the data and then keep that to themselves. So we need a mechanism where we can perform computations over encrypted data or private data such that the information is never actually seen. Now, there are three sort of classes of privacy that I'd like to discuss. The first is zero-knowledge proofs, which is something that I think everyone is at least a little bit familiar with. And these come in the forms of ZK snarks or ZK starks, but they also come in somewhat alternative forms that we classify in ZK proofs, such as payment channels, where you can have state transition or payments made in an offline channel, which is hidden only to those parties, and then that can later be revealed and attested to its correctness. However, in the ZK proof environment, all inputs for the state transition have to be known by at least one party. Whoever's constructing this proof or attesting to its correctness in the first place has to understand everything about the inputs. So we can look instead at zero-knowledge compute, which is a class of fully homomorphic encryption and multi-party computation, which allows us to perform aggregate computations on multiple sets of data from different input sources, where those input sources don't want to reveal that data to each other. And in this situation, all inputs are unknown to everyone, except for the people that put those inputs in initially. But a key thing that we would also like to achieve is that we can permission access to the answers. And finally, we have ZK storage, and this is usually quite related to ZK compute. And this is simply where we want to store our data on-chain, have it replicated, and have permission-based access to it. And this is usually related to ZK compute because our computation has to access data of some kind. So Republic Protocol's interest in privacy-preserving computation started about a year ago when we set out to develop a decentralized dark pool. For those of you who don't know, a dark pool is a type of exchange, except that the prices and volumes of the orders inside the dark pool are unknown to anyone. This includes the nodes that are performing the order matching computations. And so we needed some kind of zero-knowledge order book, some way to sort, some way to perform inequalities, some way to aggregate data from multiple traders without those traders revealing information to each other. And over our research and development to achieve this, we looked at ZK snark and ZK stark. And while these technologies are absolutely amazing, and I personally am a huge fan of Eli and his team, they only provide ZK proofs. And they're incredibly expensive to verify on-chain. Now, this makes them suitable for scalability concerns, where the verification is exponentially faster than the original computation. But when you want to provide ZK proofs for small state transitions individually, it becomes impractically expensive. There's also fully homomorphic encryption. Now, fully homomorphic encryption has a reputation for being computationally slow, but it's also slow for other reasons. If you want to provide permission-based access to the answers, you can't wait for the parties who initially encrypted the inputs to come back online. This interactive process slows the whole system down, so it's not suitable for every type of application. It also requires some kind of trusted setup if you would like multiple parties to share that encryption and not have access to the private key. And we don't know of any information theoretically secure fully homomorphic encryption. And lastly, there's secure multi-party computation. Now, secure multi-party computation gives us a lot of what we want, but it has a complex pre-processing phase where we have to generate a lot of randomness, and this is quite computationally expensive. And for reasons based on this, it is also not truly Byzantine fault tolerant in a decentralized network where you have to enable nodes to go offline. The Ren virtual machine was something that we have begun developing, which sort of addresses these three classes of privacy. We implement ZK proofs using an off-chain verification of ZK snarks with on-chain attestation, which helps us reduce the gas fees. We have ZK compute, which relies on secure multi-party computation, but it uses a new form of secure multi-party computation that we've developed, which is Byzantine fault tolerant and has a much simpler and reduced pre-processing phase. And because this ZK compute uses threshold secret sharing, we can simply leverage that again in our storage layer. So now I'd like to discuss about how we actually use or implement ZK proofs in Ren virtual machine. So you have some user or a prover, and they construct a ZK proof using either ZK snark or ZK stark, and they submit this proof to nodes in the network. Now, these nodes are economically bonded to some underlying blockchain. And this economic bond, usually in the form of staked tokens, is a good behavior bond that is a promise to behave, and if they are shown not to, they will lose this bond. These nodes perform the verification of this proof, and then they provide an attestation on-chain saying, yes, this proof is valid, or no, this proof is invalid. And at any point, anyone, including other bonded nodes, can come along and challenge this and say, no, I think this attestation is incorrect. I performed the verification myself, and I saw that the answer was actually different. Now, the moment two nodes come up with a different answer, this process will begin. But even if the nodes don't challenge each other, any other party can. Now, the key here is that to challenge a node, you then prompt the blockchain to verify the proof on-chain so that you know what the verification result truly is. But this requires quite a large amount of gas, or equivalent. At the moment on Ethereum, depending on the proof that you're trying to verify, this can take up to 1/3 or half of a block's worth of gas. But this is actually a good thing. This prevents the challenger from wantonly just challenging every single verification that they see, because they have to pay for the verification process. However, in the case that the challenger is correct, and one of the nodes did in fact lie, the bond of that node is slashed and paid back to the challenger in recompense. And this gives us a restriction that the stake of these nodes has to be at least the cost of one of these verifications. But this is how we achieve more scalable ZK proofs for small transactions and state transitions by enabling the gas fees to be paid by the malicious party if gas fees are paid at all. This is not including the attestation gas fees, which are very minimal. But it also allows applications to choose the level of security that they need. They can wait for whatever time they deem appropriate in order to be sure that the network is secure, or that these attestations are correct. Next, I'd like to discuss how we achieve ZK compute on the Ren virtual machine. Before we can discuss exactly how we do this, we have to look at how secure multi-party computation works. So to begin with, you have some party X, and this party takes a secret and they split it up into shares, and they provide each of the nodes with one of these shares. Then you have a second distinct party that wants to hide their secret from the other party and vice versa. And Y takes their secret and also splits it into shares and distributes those shares to the nodes as well. And in the next step, these nodes can perform a collaborative computation where they communicate with each other to ultimately reduce these shares of X and Y into shares of Z. What's important to note at this stage is that nowhere in this process are the original values X or Y revealed to anyone, including the nodes, nor is any node capable of seeing what the value of Z actually is. They only see shares, which is by themselves not sufficient. Then afterwards, in line with whatever rules have been put in place, these nodes can provide these shares of the answer back to X and Y. They could also provide these answers to anyone else that is permitted under the rule set. Now, state-of-the-art SMPC is not quite good enough, not for decentralized networks. And this is for three core reasons. The first is that it requires a complex pre-processing phase. Whenever you want to do a single bitwise multiplication in the online processing phase, before you do that, you have to generate 3 random values that are correlated. So to perform this multiplication, ahead of time, we have to provide a random number A, a random number B, and some number C that is the multiplication of A and B. So to perform a multiplication, we first have to do a multiplication. The only advantage that this provides is that we can do this ahead of time. However, to do this, we leverage complex cryptographic techniques such as oblivious transfer or somewhat homomorphic encryption, and it simply isn't scalable in a decentralized network if you want your throughput to be constant and available at all times. At some point in your active online processing phase, you will run out of pre-processed data, which means you have to generate new pre-processed data. And if you don't want your system to go offline while you're doing this, you have to be able to sacrifice online throughput to perform this pre-processing. So we cannot simply ignore the cost of pre-processing. Secondly, in the online phase, to assure that the computations that are being done were done faithfully and were not corrupted by any malicious actor, we have to rely on non-threshold secret sharing. This means that not a single node can go down, but it also means that whatever our zero-knowledge storage mechanism is, which should allow for nodes to go down and the data not be lost, has to undergo a translation phase before it can actually be computed. And this adds again to processing time. And lastly, and perhaps most importantly, is these techniques are not truly Byzantine fault tolerant in a decentralized setting. Not a single node can go down and the computation survive. The computation either stops and is aborted entirely, or it has to be restarted all the way from the beginning. Now, this is a problem in decentralized networks, because before we even consider potentially malicious parties, we have to consider that in a decentralized network, our nodes are distributed geographically around the entire world. Network partitions will happen, and nodes will stop being able to see each other. Nodes might go offline in order to be upgraded. We also might see that a single node is currently under attack. So instead of having no single point of failure, we instead introduce a single point of failure at every single processing node. And this simply isn't good enough for decentralized networks. In the Ren virtual machine, we rely on threshold secret sharing throughout the entire computational phase. This allows our nodes to go offline at any point in either pre-processing or online processing. It also allows us to drastically reduce the pre-processing complexity. We only have to generate 1/3 of the data by comparison to modern techniques, but that production is also much, much faster. And we've been inspired by the practical Byzantine fault-tolerant techniques, specifically an implementation called aardvark. So in the pre-processing phase, nodes undergo an election stage where they find a primary replica that will lead the pre-processing computation. At any point, if this replica goes down, they can simply move on to the next leader. And they can do this efficiently by relying on the underlying blockchain to define an ordering that can be shuffled deterministically. Once a leader has been elected, the leader sends out a request for pre-processing data. And this pre-processing data is a share from each node for each other node. Once this request has gone out, each of the nodes will respond to the leader. Now, in these two phases, the request-response cycle, up to 1/3 of the nodes have to be online. But this means that up to 2/3 of the nodes involved can go offline. And the pre-processing phase can still continue. What's more is that the leader then aggregates these responses and returns them back to the nodes. The leader will not aggregate less than 1/3 of the data. But if it achieves more than 1/3 of the data required, it can send this to every single node and actually recover from lost nodes that have gone offline and have potentially come back online since. Now, one of the cool things about this is that because we rely on threshold-based secret sharing, we can leverage that again in our storage layer. We do not have to undergo a translation phase from the storage of data to a format in which we can perform computations on that data. And this drastically speeds up the processing by comparison to modern techniques. And we can achieve permission-based access to this data by leveraging the compute to perform checks and balances to make sure that the people that are requesting access to this data are the only ones that are getting access to this data. And throughout this entire process, through all this storage and processing, we're resilient to up to 1/3 Byzantine actors, which is in line with the theoretical threshold when you do not rely on computational security. So using Ren Virtual Machine, we're able to improve upon the decentralized dark pool that we've built. Now, we've already built this thing, the dark pool, and it's available now on mainnet, and you can trade there at ren.exchange. But using Ren Virtual Machine, we can take this even further. We can provide a faster order matching engine. We can provide completely private balances. Before traders even open their orders, we can verify that they have the balances necessary, and we can do this without the traders having to reveal their balances. We can also provide completely private settlement. Once orders have been matched and it's time for traders to settle and exchange funds, they can do so without revealing that transaction. And what's cool about that is this can be done regardless of whether the underlying tokens being used are actually zero knowledge themselves. You don't have to be relying on a system like Zcash that is already zero knowledge compatible. We can also expand it to some more interesting ancillary features, such as providing atomic swaps for cross-chain settlement without having to rely on hash time lock contracts that could potentially lock your funds for up to 24 hours. And you can even have these atomic swaps happen privately. But we can do so much more than this. With Ren Virtual Machine, we have a completely general compute engine. Whatever you want to build, you can build on RenVM. You can develop zero-knowledge voting systems. You can develop zero-knowledge decentralized finance of any kind. And you can also build applications that consume data from large sets of users and perform high-level analytics on that data, such as in the health industry, without ever putting the data of those users at risk. So with Ren Virtual Machine, we achieve a generic private computer that can be used to build absolutely anything that you dare. Thank you.
네, 질문은 다 끝나고 해주시면 되겠습니다.